Okay, students, video number 2 from chapter 20 has to do with the properties of carboxylic acids and the acidity of carboxylic acids. And this lecture is particularly important for those people who are going to go on to biochemistry because it explains a lot about human physiology and the pH of human physiology and organic compounds within the human body. So let's take a look at that. It turns out that carboxylic acids are very high boiling compounds. So if we were trying to boil off some carboxylic acid in a beaker, it would take a lot of energy for them to boil. The reason why is because carboxylic acids normally hook up in dimers. The reason why they do so is because they're going to have hydrogen bonding between the hydrogen of the OH group and the carbonyl group. And that's going to happen on both sides. So this dimer is going to require a lot of energy to break apart those intermolecular bonds in order for it to be in a vapor state. So they're very high boiling. In addition, carboxylic acids tend to be very acidic compounds. When we talk about acidity, for the most part, you're used to the idea of a pH. The lower the pH is of something, the more acidic that compound is. The higher the pH of something is, the more basic that compound is. But there is a relationship between the pH of a solution, that means the acidity of that solution, and the pKa of the acid that is in that solution. The pKa of the acid that is in the solution basically tells us a little bit about the hydrogen that is in question. That is the most acidic hydrogen that is in that solution. Hydrogens that are attached to a carboxylic acid functionality, we already know are very acidic. If we use aereo like we have been all year long, we know that by taking away that hydrogen, we create a carboxylate, ending in an ATE, a carboxylate which has a resonance stabilized resonance structure. We've also learned to realize that this is not a real negative charge. It's really only half of a negative charge, separating that charge between two different atoms, both of which are very electronegative, meaning that this hydrogen is very acidic and can be pulled off fairly easy by even a mild base. If we compare that to something like an ethanol, we know that we can remove the proton on ethanol, but that's going to give us an oxygen with a negative charge. Even though oxygen is very electronegative, and this is much more stable than other things, it still requires a lot of energy to have an oxygen with a negative charge. If we look at this specifically in the form of pKa's, and I'm not really big on pKa's. I'm much better at just asking you to recognize that this is more stable than this, therefore this is more acidic. This is more acidic than the corresponding alcohol. The problem is that at some point we do have to get a ballpark idea of how much more acidic something is. And to be able to do that, we can only do it by using its pKa's. So as an example, the pKa, or what a pKa is the measure of the acidity of that acid. The pKa of this hydrogen is 4.75, whereas the pKa of this hydrogen is somewhere closer to 16. Now, here are two numbers. We know that the closer the number is to a lower number, to 0, it's going to be more acidic. The higher the number is, the less acidic it's going to be. But it still doesn't give us a very good idea of what is the relationship between the two. This is where the Henderson-Hasselbalch equation comes in. And I know I have to take you back to general chemistry, but it's really going to help you to understand the relative acidity of things. So let's go for a minute to general chemistry and let's look at the Henderson-Hasselbalch equation and see if I can explain to you what the equation means, not how to use it. I am not going to ask you any questions about using the Henderson-Hasselbalch. You already did that in general chemistry and mastered the material. But I want you to understand the equation, not necessarily to be able to do calculations. By understanding the equation, it tells us that a pH of a solution is equal to the pKa, or the acidity, of the conjugate base divided by the acid. But what exactly does that mean? It means that for anything other than really, really strong acids, so when we were in general chemistry, we were looking at acids like HCl, H2SO4, and so on and so forth. These acids are strong acids and dissociate completely. So their pK, or their pH, is directly equivalent to the concentration of the hydronium ion in the solution. No problem. If you have the concentration of the hydronium ion, you can figure out what the pH is. It's not very difficult. The Henderson-Hasselbalch equation is really meant for organic acids. Organic acids are not completely dissociated. Sometimes they are somewhat dissociated, sometimes they're not dissociated at all. The hint that we can find is that if we know the pKa of an organic acid, we can estimate at which pH that organic acid is going to be deprotonated or whether it's going to be protonated. Now that's a bit of a large concept, but let's take the idea of acetic acid. Acetic acid has 2 carbons, has the carboxylic acid. If I put this compound in solution, it's only going to be somewhat deprotonated. How deprotonated it is directly related to the pH of the water. What I do know from this equation is that if the conjugate base is equal to the conjugate acid, then this is equal to 1. So if I have equal amounts of a carboxylic acid that is protonated and a carboxylic acid that is deprotonated, and I have equal concentrations of those 2 compounds, then this becomes 1, and the log, oh, I forgot a log here. The log of this number is equal to 0, because the log of 1 is equal to 0. So this whole factor gets canceled out, which means that at a solution where you have 50% of the protonated compound and 50% of the deprotonated compound, your pH is equal to your pKa. This magical point at which your pH is equal to your pKa, in the case of acetic acid, that would be 4.75. This point is referred to as an isoelectric point. You'll learn a lot more about isoelectric points in biochemistry. But for now, let's take that concept of the pH and the pKa being equal at a specific pKa. That tells me that every time I increase the pH from 4.75 to something higher, I'm reducing the amount of this compound in solution, because the higher the pH, the more basic. In fact, because this is a logarithm and it is a base 10 logarithm, it tells me that I should be able to predict the amount of this and this that is in solution depending on the pH. For instance, at 4.75, there is 50% of each one of these. If I increase the pH to 5.75, what have I done? I've increased the pH by 1 whole unit. That means I'm making it more basic. If I make it more basic, for every 1 unit of basicity, I increase the ratio by 10. So now, at pH of 5.74, I am going to have 40% of the protonated, and I'm going to have 60% of the deprotonated. So I've gone from a 50-50 ratio to having a 40-60 ratio. Now I'm going to increase the pH 1 more unit. I'm going to go and I'm going to look at the pH now at 6.75. Well, if 5.75 has changed this from a 40-60, it seems kind of logical that the 6.75 would be a 30-70. But that's where you would be wrong. Because it's logarithmic and exponential, you're adding a 0 to this factor. So all of a sudden, I'm going to have 100 times more. So let's take a look at it in a more realistic fashion. If the ratio, and that's what we really want to know, the ratio of these compounds is 1 to 1 at a pH of 4.75. At a pH of 5.75, the relationship is going to be 1 to 10. There will be 10 of these for every one of those. And if I increase the pH to 6.75, there'll be 1 protonated versus 100 deprotonated. By the time I get to 7.75, there's only 1 in 1,000 that's going to be protonated. So by looking at this, and you very much have to do this on the MCAT, you have to guesstimate and estimate the percentage. Every time that you go up 1 pH, you're increasing it by 10. So a difference of 2 pHs is a difference of 100 to 1. I hope that clarifies the Henderson-Hasselbalch enough for you to be able to get all those questions on the MCAT correct. Until our next topic, this is Dr. Bordas.